Let's move on now. We're going to look at some more properties of limits. This property we've already seen. It's a corollary to the product property or the product law, where when a constant is multiplied with a function, so limit of a constant times a function is equal to constant times the limit of that function. That's the third property. Then we have the power law and the root law. These are also considered, so the power law is also a corollary of the product property. I'll show you how. See, we all know that limit of f of x into f of x when x tends to a number is equal to limit of f of x as x tends to a multiplied by limit of f of x as x tends to a. Isn't this same as saying limit f of x tends to a whole square? Okay, if you have n number of functions, if fx is multiplied by itself n number of times, then you have this rule. Simple as that. Okay, take a close look at this rule. So it says limit of f of x to the power n is equal to limit of f of x. Let's say this value is L. Limit of f of x whole to the power n. So the answer is going to be L to the power n. Similar thing happens when we are dealing with root. So square root of f of x, limit of square root of f of x would be equal to square root of limit of f of x. Similarly for cube roots and so on. Okay, one important thing to note here is if n is odd, then we have no problem. But if we have to find, let's say, the fourth root of a function, we need to ensure that whatever is inside the square, inside the root sign, whatever is inside the root sign, that must be positive. Otherwise, roots are not defined, right? Roots of negative numbers are not defined. We'll have to go into complex numbers then. So that's why we need to ensure that L or whatever is coming here, that must be positive. Must be positive. This is only in case when n is even number. When n is an even number. Okay, I want you all to just take a look at these three properties. Pause for a moment, take a look at all these three properties. Let me clean this screen. Okay, yeah. If you want, you can take a screenshot or make a note. And we're going to find limits now. Now, this is the actual exercise this session culminates into. So we have four very simple questions, very simple functions. We're going to see which property is being applied where, and we're going to find out the limits. Finding out the limits is really easy. It would seem like just substituting the numbers gives you the answer. But I want you all to realize which property is being applied here, which algebraic property of limits we are applying when finding out these answers. Let's look at the first question. Okay, first pause the video, attempt these questions on your own. Pause it for 5 minutes or so, that's all it will take, and then resume the video. Okay. I hope you all have given it an attempt. If you have, let's get started with the solutions now. The first question, limit x square plus x cube. Now, which of the three properties that we studied at the start, which property are we applying here? We have two functions. Let's call this f of x Let's call this g of x. We have two functions, f of x and g of x. What we have to find out is the limit of sum of these two functions. This is equal to the sum of limits of these functions. So sum of limits of these functions. And what are those things? You just substitute the value x equal to 3 there. You'll get 3 square, and here you'll get 3 cube. Okay. So it's 9 plus 27 and that's your answer. All right. Now, doing this for the first time, you will feel that, it's futile to split it like this. Why can't we just directly substitute x equal to 3 here itself? I'm sure many students would have that question. Why don't we do directly substitute x equal to 3 there? We can, if we assume this entire function to be just one function, okay? But for now, I just want you to understand that when you have combinations of many functions, okay? Now sometimes, see, these are two algebraic functions. That's why it's easy to club them together into one function. But we have at times combinations of trigonometric functions, algebraic functions, logarithmic functions, and so on. Now, in those cases, we'll have to find out the limits of those functions separately. That's why, and that's where these properties will come in handy. These properties, the understanding of these properties will be important to solve such questions. For example, if I asked you a question, what is the limit x tending to 1 sine x plus x cube? Then you won't have any other way but to split it like this, but to use the property. So you must use the property here in order to attempt questions like these. Okay. So for now, let's keep doing this. Okay. Limit of 5 into x cube. You see, it's the fourth limit that we studied, which is when a constant was multiplied with a function. This limit is equal to that constant times limit of this, which is 5 times 4 cube. Okay, 5 times 4 cube. Yeah. So you can write it like 5 into 4 into 16, and just for easy calculations you can do it whichever way you want. This is 20 into 16, it's 320. Okay, so that's the answer for the second question. What about the third one? Let's pick another color. A function's whole cube. A function's whole cube. We have to find the limit of that function. So this would be limit of this function and you find out the whole cube of this. That will give you the answer. So this is 10 whole cube, this is 1000. All right, let's find out the limit of the fourth one, where x tends to -1. Please note, this is a negative number. Okay, what happens here? This is a quotient of the two functions, right? If you assume this to be f of x, you assume this to be g of x, there's one thing you have to ensure. Limit of g of x should not be 0. If the limit of g of x is coming out to be 0, then you cannot apply the property that we have studied. But we don't have a problem right now because limit of g of x is not 0. We can see that if you put -1 here, limit of g of x is coming out to be 4. Okay, let's solve this now. Limit x cube -1 upon limit 4x square. I'm skipping this part because this just clutters the board for now. But we know that we have to substitute minus 1, okay? So this is minus 1 whole cube, this thing. And here we have 4 into minus 1's whole square. Minus 1 whole cube is minus 1 on the top, and here we have 4. This is minus 2 by 4 minus half. That's your answer. Okay, minus 1 by 2. Okay, we're almost coming to the conclusion of this session, and but before we proceed, I want to discuss the limit of polynomial functions. We're going to encounter many algebraic functions, specifically polynomial functions, where we can directly substitute the values and find out the limits. So in general, whenever we have a polynomial function, we can substitute the value. We can substitute the value directly, and that is what is shown here. Why that works. So this is the general form of a polynomial function. If you want, you can take an example. Let's say 2x cube plus x square plus 5. Okay, let's say as an example. This is an example. What happens if we have to find out the limit of such functions? What we've done here is we've used the properties to show that the limit of f of x at x equal to a is same as the value of f of x at a. So limit of f of x at x equal to a is actually equal to f of a. What are the properties that we have used to prove this? See, this is the fourth property. When a constant was multiplied with a function, its limit was the constant number multiplied by limit of that function. We've repeatedly used this property on every term of the polynomial. Also, overall, we've used the first property, that is the property of addition. If we have sum of different functions and we have to find the limit of combination of such functions, which are sum of different functions, we get this. So two properties basically. The first one, I'll just list down those properties, what we've used here. To show that the limit of any polynomial function is actually the value of that function at x equal to a. Now this is a very important result. This is our result. That limit of a polynomial function at x tending to a, when x tends to a, is same as the value of the function. This is value of the polynomial at x equal to a, and this is limit of f of x as x tends to a. And what are the two properties that we used? Limit c times f of x is equal to c times limit f of x. This was one property we used. The other property that we used was limit fx plus gx is equal to limit fx plus limit gx. Now if there are n number of functions being added, we just split it those many times. So if we have limit of fx plus gx plus hx, then we split it as limit fx plus limit gx plus limit hx and so on. So that is what we did here. We split it those many times, see, and then we applied this property on every term to show that the limit of any function, the limit of a function at x equal x when x tends to a is same as the value of that function when x tends to a. Okay, I see that this part is not visible, so I'll write it again. Limit of f of x as x tends to a. This is this one and this is this. Okay, with this understanding, let's quickly solve a few questions on polynomial limits. Now we know Now we know that directly substituting this value will give me the answer. Okay, we have been seeing this for quite a while, but now we know why this works. So limit of this is actually 3 times minus 2 whole square plus 5 times minus 2 minus 9. You figure out the answer to this. 3 into 4 plus 5 into minus 2 of course, and minus 9. 12 minus 10 minus 9. This is 2 minus 9, which is going to be minus 7. Okay, so similarly you can find out the values of polynomial functions. Now the second question, taken in entirety, is not a polynomial. This is not a polynomial. Still, I have put it under the heading polynomial functions because it's a division of two different polynomial functions. Okay, it's a division of two different polynomial functions. Let me show how. You tell me, is this a polynomial function? Yes, it is. Let me call this f of x. Similarly, this one is also a polynomial function. Let's call this g of x is also a polynomial. Okay, this is also a polynomial. So now to solve this, we're going to apply the property as well, and we are going to apply this trick also. The trick where we learned that to find the limit of a polynomial, we can just find the value of that function at the given point. So let's find out the value now. This, we first apply the property we learned at the start of this session. What was the property? Limit of f of x upon g of x can be written as limit of f of x upon limit of g of x. So limit 6 minus 3z plus 10z square and upon limit of the second function minus 2z to the power 4 plus 7z cube plus 1. Okay, all we need to do now is find out the individual limits of the numerator and the denominator. To do that, you just substitute the value x equal to 1 in place of z and you will get the answer. Let me do all this directly now. 6 minus 3 into 1 is 3 plus 10. This is in the numerator. In the denominator, we have minus 2 plus 7 plus 1. What do we get? 16 minus 3, that's 13. And here we have 8 minus 2, 6. So 13 upon 6 is the answer. Okay, so that is it. Okay, so 13 upon 6 is the answer. We're going to pause here. After this, we are going to look at finding out the limits of functions using algebraic manipulation. This is what we are going to study next. How to find different limits of different functions using algebraic manipulation. But the question arises, why is algebraic manipulation needed at all? What are algebraic manipulations? What are different types of algebraic manipulations? How do we use them to find out the answer? All those things we're going to do in the next session. But just to give you a glimpse, there are certain manipulation techniques like factorization. Uh, you find the limits, you find the LCM, then you use the conjugate of a function to find, and then there is L'Hopital rule. All these things we're going to do in the next session. Uh, for today, I think we've covered quite a bit. So we'll take a pause. Thank you so much for attending these sessions, students. Do let me know in the comments section if you want me to explain things in a greater detail, or you want me to increase the pace of the session. Uh, yeah, do let me know whatever you think of the session. Okay. Thank you so much for joining. Bye bye.